我能不知道？我就看第一。
是下星期三就的。
27号交的是，那不是下周，我不是这周不交，是下周。对，那个就可能就那么一本书叫人借去了，那我没办法，你也弄不着那个题呀。我还想问问别人，我说想上图书馆催催，能不能把那书赶紧还过来？太老了。
他好像没有年龄。
没有，就是那有一本叫人借去。他要是说有那啥也行，就是说图书馆有不让借出来，在那里看，那你可以复印的呀。
对啊。
那你放假回家你随便交钱？
那就交是吧？
交1个月。
交了2个月。
交2个月。
给他租。那时候也租不出去，没人想短租。那假期的时候，没人想短租。
但是你要是木的话，又不方便了嘛。
对呀，我东西还得放在别人家什么，然后现在搬到别人家，别人家我回来还得找房子，可以干嘛嘛？而且9月初回来还能找到房子，牺牲那么多。
找不着。
我也想搬下去。
怎么不好？
不太想，过一段毕业了。
All right, so we have a very short section now, section 1.3 in chapter 1, which talks about vector calculus, or fields and their derivatives. So in general, what I'm interested in is objects in 3D. And on those objects, I'm interested on I want you to look at the object as if it's TV. And on this TV, you can see all sorts of maps. I can see a map that tells me that the temperature here is higher than the temperature here. The temperature here is a certain value, the temperature here is less. The gradient for, or contour plots of temperature. The temperature would give me a value for each point in that picture. So a scalar field is a map. If my object is a set in R3, set of vectors, the temperature would be a map that any point in T, in D, will give me a real number. This is a scalar valued field. Tell me what the point is, tell me the vector inside that material, and I'll tell you what the temperature is. I'm also interested in maps that tell me, that give me vectors on my object. The displacement, for example. D is a set in R3. For every point in my object, I have a vector. For example, the displacement of that point. This is a vector valued theta. For every point on my object, I can give you a matrix. The matrix here is different from the matrix here. The matrix here, so the matrix depends on the point. And I can have a map from every point that gives me a matrix. In our applications, T, phi, and U are continuous and smooth functions. I will not define smoothness because that's a huge, or continuity, because the definition, it's a huge definition just to say what a continuous function is, especially when you go to higher dimensions. But you just have to visualize it. If you just take it, if you imagine that it's in one dimension, the distribution of whatever the stress or the temperature or anything is a smooth function. Since they are smooth and continuous functions, and since my object is described using coordinates, I can describe these maps using coordinates, which means phi becomes phi of the vector x becomes a function of the coordinates the displacement at a point inside the material x is a function of the coordinates and the matrix at a point x, all the entries of this matrix, each entry will be function of the coordinates. Sorry, I called it T. And we are going to define a few things that we are going to need in the future. And the first thing that we're going to define is the gradient of a scalar field. For example, the temperature, if this is the temperature distribution on an object, where the temperature is 40, 30, 20, whatever, the gradient of the temperature field, or that scalar field, is a vector, telling me where is the direction of the maximum change. And the maximum change is usually perpendicular to those contours. So you get this map of vectors. So if phi is a scalar field on a set D in R3, then the gradient of phi is defined as partial phi by partial x1, partial phi by partial x2, partial phi by partial x3. A vector with 3 components. And this vector gives me the direction of the maximum change in that scalar. For example, if you have a constant temperature, the gradient of phi would be equal to 0, which means at every point you get a 0 vector. Temperature is not really changing around. If you have phi that's only function of x1, it's only changing in the direction of x1, it's not changing in the direction of x2, you get the vectors, let's say phi. The temperature is equal to 50 x1. Tell me what x1 is. The temperature increases as you go in the direction of x1, then the partial phi. Then the gradient of phi will be equal to 50 and 0, which means temperature is only changing in the x, it's not changing in the y. And you get vectors horizontal. Now gradient, or this gradient of phi, is a vector that is first order tensor. Because if I change the coordinate system, if instead of x, I use x prime, where x prime is the new components in the new system, you will find that the gradient of phi prime in the new point system will be equal to q, the gradient of phi. Because partial phi and partial x prime is equal to partial phi by partial xi, or partial phi by partial x, multiplied by partial x by partial x prime. If you do it by components, you will get, well, I'll do it by components just so that you guys, if you have to do it some other time. Partial phi by partial xy, xi in components will be equal to partial phi by partial xj multiplied by partial xj partial x prime I, where I'm summing over j. And from here, you get that partial phi, that partial x prime I, or partial x prime, will be equal to q partial phi by partial x. The gradient, before we jump, the directional derivative. If I have a scalar field or scalar, sometimes I'm interested in the derivative of this scalar field in this direction n. I would like to know the rate of change of that temperature in this direction. To find the rate of change of temperature in a certain direction, or the rate of change of a scalar field in a certain direction, so the directional derivative, this is vector x, then the rate of change of that scalar field phi that takes from D to R is equal to the temperature at a distance, at a very small distance in the direction of n minus phi of x divided by h. So I'm just going to slightly move in the direction of n. So instead of x, I'm going to take x plus a small distance h in the direction of n minus phi of x divided by h. This, using a Taylor expansion, because phi is smooth, this will be equal to partial phi by partial x multiplied by h n plus phi of x minus phi of x divided by h, again limit as h tends to 0. Phi of x will cancel phi of x, h will cancel h, and you'll get the dot product between partial phi by partial x and n. So if I have phi, the gradient of phi, or phi, the gradient of phi, which is a vector, if I want the directional derivative of phi in any direction n, all I have to do is just take the dot product of phi with respect to n. So for example, the temperature is function of x1, the gradient of phi is 50 and 0, which means the contour plot will look like this. The gradient, the plot of the vectors will look like this. If I want to know how much phi changes in this direction, partial phi by partial x dot n will be equal to 0. Phi does not change in this direction. If I take n equal to 1, 0, partial phi by partial x dot n will be equal to 50. So the rate of change of phi in this direction is, the directional derivative of phi in this direction is 50. And so on. You can find any vector. Let's call this n1, n1, n2, n2. And that's it. You can find the directional derivative of phi in any direction by simply picking the vector and taking the dot product between phi, the gradient of phi and this vector will give you the rate of change of phi in that direction. Gradient of the vector phi. The gradient of a vector field is described as follows. If I have u, which is equal to, which is a map from D to R3, for every x in D, there exists a vector in R3 such that this vector is equal to function of x, or in other words, any vector here, x, I have a vector here, so I have lots of vectors, it's a vector map. The gradient of u is defined as follows. it's a matrix, it gives me, as we will see later, it gives me something about what is happening at this point. And we will use this to utilize this gradient. Once I know the displacement, the gradient of the displacement tells me something about the strain, as I will explain in a second. If I change the coordinate system, so the gradient of u is a second order tensor. If I change the coordinate system, the gradient of the new components of the gradient of u will be equal to q, the gradient of u, q transpose. So, right. So, if, just example, let's say my vector field represents the horizontal displacement of an object. The object is moving horizontally, and every point is moving the same distance. If every point is moving the same distance, what do you expect the gradient of u to be? 0. Since u is constant, the gradient of u is 0. The strain, when we discuss the strain in chapter 3, will be derived from this matrix, the gradient of u. I expect that I only see strain when points start moving with respect to each other, not as they all move together with the same displacement. You only see strain when one point moves more than the one before it, when only the gradient of u start having non-zero entries. Divergence of vector and tensor fields. If I have a vector field, u is a vector field from D to R3. And a tensor field from D to M3. U is a function of x1, x2, x3. And T, the matrix, is a function of points under consideration, x1, x2, or x3. The divergence of u is defined as partial u by partially 1 by partial x1 plus partial u2 by partial x2 plus partial u3 partial x3 and the divergence of t, so this is a scalar, and the divergence of t is a vector defined as follows. The first component has this entry, the second component has this entry, just a word of caution. In some, depending on the book that you're reading, sometimes these are reversed. So follow this definition. Some other books would be partial T11 by partial x1 plus partial T12 by partial x2 plus partial T13 by partial x3. The following definitions, I will not need them, but I think you might be, the geotechnical students might need them, but it's just they're just definitions. If I have a vector field, curl of u is a vector, it's equal to the following: partial u1, u2, a partial x3 minus partial u3 by partial x2, partial u3 by partial x1 minus partial u1 by partial x3, and partial u1 by partial x2 minus partial u2 by partial x1. Or in component form, curl u, the component I, is equal to epsilon I j k partial u uj by partial x. And if I have a scalar field, then the Laplacian of phi is equal to this. So common notation is used throughout to make things a little bit easier, the notation easier. So the gradient of phi is a vector, so let's remember the gradient of phi was equal to partial phi by partial x1, partial phi by partial x2, partial phi by partial x3. The component I in the gradient of phi is equal to partial phi by partial xi. I can write it phi, comma I. The gradient of u was equal to a matrix. If u is a vector field, the gradient of a vector field was a matrix made out of partial u1 and partial x1, partial u1 and partial x2, and so on. So the gradient of u is a matrix with components ij, which is equal to each component is partial ui by partial xj. I can write this ui, comma j. This comma notation, comma means partial ui with respect to xj. The divergence of u, when u is a vector field, was equal to partial u by partial x1, u1 by partial x1, plus partial u2 by partial x2, plus partial u3 by partial x3. So the divergence of u is equal to partial ui by partial xi, where summation is implied, which is ui, comma I. divergence of T, where T is a matrix. Divergence of T was given as follows. The sum of partial T J1 by partial xj, j equal 1 to 3. Partial T J2 by partial xj, j equal 1 to 3. So it's a vector with components I. These components are equal to partial T J I with respect to xj, which is equal to T J I comma j. J is repeated, there is sum, I is repeated, therefore it's sum. The Laplacian of phi, which was equal to the sum of partial phi by partial xi with respect to xi when I is equal to 1 to 3. The Laplacian of phi is equal to phi with respect to I twice. And I is repeated, so it's sum. The last section that we're going to cover today is the divergence theorem. Or the last section in linear algebra that we're going to cover today, or in the whole course, is the divergence theorem. So what is the divergence theorem? The divergence theorem is an extension of the, I think it's called the fundamental calculus problem. I'm not sure what the exact name, but it's an extension of the following to 3D. If I have the rate of change of a function with respect to x, if I have that rate of change everywhere, every time I multiply partial f by partial x multiplied by delta x, I get a small change in the height. If I keep going all the way, if I sum, this is equal to the summing of the delta h's. Which will tell me something about the difference in the height between, if I call this f2 and I call this f1, I will get f2 minus f1. So what did I do here? I used the gradient inside my domain from x1 to x2. I used the gradient inside of the domain to tell me how the function changes on the outside of the domain. This is the boundary of the domain, this is the boundary of the domain. f2 minus f1 tells me the integral of partial f by partial x dx gives me f2 minus f1. So we know this from calculus. Now we want to extend this into three-dimensional objects. And here, instead of something changing, instead of the domain being only a one dimension, the domain will be an object, a volume. And the divergence theorem states the following. I don't know if I don't have it here. So I'm going to write it. I have a set V in R3. And its boundary S is equal to, or indicated like, so I have an object, V, and its boundary is called S. On the boundary, I have a unit vector called N. And phi is any scalar field defined on V. Phi is a function of capital X, where capital X is the coordinates of the point inside the volume. And the divergence theorem states the following. If I integrate how much phi changes with respect to x1 inside the volume, I'm going to get something on the boundary. This is, I don't have one point, I don't have 2 points, I have the whole boundary. So I'm going to integrate all this on the boundary. But because I'm taking partial phi by partial x1, I'm only looking at the variation of phi with respect to x1, I will get phi n1. And the proof is omitted. If you just look, just do a quick search on the internet, and there's lots of, just the proof is very long. And it just utilizes this fact. It's just an extension of this to three-dimensional objects. Also, partial phi by partial x2 dv will be equal to phi n2 ds. Partial phi by partial capital x3 dv is equal to the integral phi n3 ds. Where n1, n2, and n3 are the components in the horizontal direction, vertical direction, and third direction of the unit vector on the boundary. N, which is equal to n1, n2, n3, is the unit vector on the boundary. So last year, there are a few bonus exercises after this divergence theorem. And last year, I asked them one of those bonus exercises, and they're very simple to do. But you need the divergence theorem, use the above, to show the following. The integral of the gradient of phi dv is equal to phi n ds. Okay, what is it that you see here? This is a vector, so I'm integrating a vector, which means I'm integrating each component. I'm integrating each component of that vector, so you have to look at each component on its own. Integrating, and then you get a vector. So each component should get the corresponding component on the other side. divergence of u dv is equal to u dot n ds. Now if you divergence of a vector, is this a scalar or a vector? Was a scalar. It was equal to partially u1 by partially x1 plus partially u2 by partially x2 plus partially u3 by partially x3. So if you treat each component using the divergence theorem, you should get this out right away. The divergence of t was a vector. If I integrate each component on its own, I will get T transpose n ds. This I will use for stress, and this I will use for the virtual work at the end of the term. And so you should know how to do these. And there are some examples throughout, just to show you that the function of those examples, the numerical examples I've drawn. The function of the numerical examples is just for you to visualize all these quantities in space. You have a vector field, you integrate this vector field, and you get a value. So look at all these examples in your book. Do you guys have any questions? Now, no questions. So the remaining parts of the course, not all, but most of the remaining parts of the course will be more, hopefully will be less boring. Because we're going to talk about concepts that you have heard of before. And you can actually, this is actually lots of fun, but you have to do it by hand. I mean, I'm having lots of fun writing and proving things. You guys are not. But hopefully the rest of the course will be a little bit more engaging because it's concepts that you already have heard of. But all the remaining concepts, or most of the remaining concepts, rely on everything that we talked about so far. Everything else is just an example of what we talked about until today. So I'm not going to cover stress today. And next lecture is cancelled. And the assignment is due the week after. The week after we're going to cover stress, and then after that we're going to cover strain. And so starting next lecture, I might go a little bit faster, simply because they're just examples. So you have to, so when I talk about principal stresses and principal strains, I'm not going to revisit that there are 3 eigenvalues and eigenvectors. You already know that. I spent a lot of time here telling you we have 3 eigenvalues and 3 eigenvectors, perpendicular eigenvectors. When I talk about the stress matrix, you should know right away what I'm talking about. Okay? So we'll see you in 2 weeks.